Okay. Thank you everyone for joining. And huge thanks to IFA for having us. We still don't have the internet connection, so thank you. And today's guest of honor is Professor Rob Wittenmyer from the University of Southern Queensland. And Rob is the PI of Minerva Australia's array of telescopes, which is used to confirm planets, measure their masses, these sorts of things. Rob is visiting Gemini this week. And today he will talk about his work, how large planets affect smaller ones, and what role does Minerva Australis play in this story. So, Rob, take it away.
Okay. Well, morning. This is the first time giving a talk to a virtually empty room. Okay. All right. So yes, so I'm Rob Wittenmyer, and I'll be talking about the importance of giant planets as a key to finding Earth's understanding Earth. Everyone loves to talk about Earth. So we're on the slides in advance. Ooh. Okay, buttons don't work. Right. Okay. So in the beginning, the universe was created. So let's start at the beginning. It's not everyone is a planet person. And so those of you who don't like planets, we do. Solar system is basically the sun, Jupiter, and some bits, right? And so we've also found that Earth-sized planets are everywhere, but the real question is, are they Earth-like? Those are two different things. So Jupiter analogs, I'm going to hopefully convince you in this talk today. Jupiter analogs are the key, and I like Jupiter analog. I just think they're neat, so that's what we're doing. So brief outline why Jupiters matter. One, of course, is that giant planets are giant. First rule of tautology club, right? So because they're giant, they're the dynamically dominant bodies in the system. They basically, the 600-pound gorilla, they tell everybody else what to do. So that drives the system architecture. So that's why giant planets are important. Number two, if you have a giant planet, that mass will fling asteroids, comets, and other bodies around, and that can deliver water to inner planets. So there's a stylized artist rendition of me destroying a planet. Someone photoshopped my face onto a meteor. In my past life, I destroyed some planets before I started finding them. I should finish my PhD, -2 planets. Yeah. And then number three, if you have a giant planet in the habitable zone, then that would be a very bad thing for trying to find an Earth in the habitable zone. So you want to make sure that you don't have one. Because of course, if you have a Neptune or a Saturn hanging out there, you're going to have a bad time. So, okay, for the non-planet people, there's soothing music with this, but it's not terribly important. You can hum if you want. So what we got here is a sort of schematic cartoon of the planetary system architectures that we know about. This is mostly from Kepler, so good representative sample of how diverse planetary systems are. Solar system is to scale, and for the Zoom people, you can't see me pointing, but it says solar system. So that's to scale, the inner 4 planets, space to scale, and then all these other systems are the Kepler known multi-planet systems. The idea is just to show you that multi-planet systems are everywhere, but they really don't look a lot like our own solar system. Some of that, of course, is a detection bias. Yes, I get it. But also, it seems that the universe likes to make systems of compact planets, as illustrated very artfully here. So Jupiter analogs also, things that are giant planets that are orbiting in, beyond say 3, 4, 5 AU, things like that are pretty uncommon in the overall scheme of things. So this nice pretty plot here by some joker in some paper a few years ago shows that about 5 to 10% of stars host what we would call a cool Jupiter or Jupiter analog, depending on how you want to call it. In this case, these two papers, they give you numbers around 6 to 10%. And yes, it's sort of me patting my own back and giving myself the medal, but it's not just me that says this. There's a whole host of literature out there. And we're all kind of on the same page here, which is to say, cold giants, things like Jupiter are not super common. And so why is that important, right? Well, our solar system contains a cold Jupiter, 2 if you want to count Saturn. So if you're looking for systems that are like ours, that's a good place to start, right? Jupiters are easy-ish. So consensus in our field is under 10%. And again, no one can see that, but the figure of it, the fickle finger of doom, but there you go. Under 10% of stars host a cold Jupiter. So you might ask, or people have asked, okay, if you look at systems with cold Jupiters, what other planets are around? How does that drive the architecture? So some recent results, here on the left, I'm showing Marta Bryan's paper that sort of kicked this whole thing off. There's a bunch of other papers that are on this same line of, okay, let's say you have a system that contains a cold Jupiter. Those seem to be more likely to host an inner super Earth. So you saw in that first kind of speedy plot, with the animated GIF and all that, the universe likes to make super Earths. They're actually quite common. I didn't show a plot about that, but for those of you who aren't in the planet field, it's off the top of my head, it's like 25 to 50% of stars have a super Earth, and super Earths tend to be everywhere. They're the most common things in terms of exoplanets. So, but it turns out they seem to come preferentially in the presence of a cold Jupiter. Yeah, you can see me doing the dance here. So a few papers on this. I show Marta's here on the left. There's a few other references. Lauren Weiss put one out recently on the Kepler Giant Planet Search. Shows very similar results. So there are counter arguments, but we won't get into that. A lot of people are thinking along these lines that cold Jupiters seem to allow more super Earth's interior. So that's all well and good, but I got bad news for you. Turns out the universe is three-dimensional. This has made us very sad in the world of radial velocities, because those of us who do radial velocities would like the universe to be two-dimensional, right? Hence radial velocities. So people like me who go find planets and measure their masses with the radial velocity technique, as is shown in this cartoon on the left, of course, we're looking at the motion of the star to and from. You're missing a third component. So the planet that you think you see and you measure its mass, you're really getting a minimum mass, right? So if you're lucky and the inclination is edge on, like the center one, the middle panel here, then yeah, what you measure is the mass. There's no sign I ambiguity, but the universe is three-dimensional. I've lodged a complaint with the makers, but the ticket is still in GitHub somewhere. So okay, so there's an ambiguity, right? You can get a minimum mass, and you say, "Oh, I found a planet of 5 Jupiter masses." Well, no, if the inclination is, kind of nearly face on, surprise, divide by sine I, suddenly you're looking at 50 Jupiter masses or something crazy. Then your planet's not a planet, and that changes the whole thing. So why is this important? This is important because most of the known Jupiter analogs, pretty much all of them basically, just for good reasons, have been discovered by radial velocity. RV. People like me, the old dogs with the gray hair who've been doing this for 20 years, we're patient. You spend what, 10, 20 years looking at a star, and you measure its orbit or the planet's motion, and you say, okay, boom, I found the planet. And I can say the minimum mass of this planet is blah. What's shown here on the left is a bit of an old result, but it's illustrative of what's going on, right? So here's a planet, I'll put it in sarcasm quotes, planet, where 6-year orbit, giant planet, almost a Jupiter analog, called a cool, cold Jupiter. And we said, okay, not we, but the authors said 9 Jupiter masses. That's great, but then later on, FGS astrometry from HST found the true inclination of the system, 4.1 degrees. And for us in the planet world, I know it's different for the star people, don't ask, historical reasons. In the planet world, an inclination of 0 is face on. An inclination of 90 is edge on. So when we say a low inclination system, 4 degrees is nearly face on, boom, that gives you a huge sine I factor. It's a star, not a planet. And there's the astrometry result that shows, okay, as the inclination gets lower, obviously the true mass gets much larger. That is a bad thing if you thought you found a planet. Another one bites the dust, right? Super Jupiter becomes a star, right? And again, this is one of ours, so I'm just gonna own it. We, in Kane and Stephen Kane and the rest of us, we did a paper and we said, oh, look, here's an orbit. It's enough of it, we could fit an orbit to it and say there's a planet 30 years, 18 Jupiter masses, okay. Big planet, small brown dwarf, whatever. Hipparchus Gaia comes along, Alex Venner ruins the day and says, sorry, face on, it's a star. Why is this important? I mean, I could go on for days on this. It's important because if you're doing demographics and you want to know which systems contain cold Jupiters, you do not want to have, a quarter solar mass M dwarf hanging out in there, mucking up your statistics. Not a good look. So this is why it's important to actually know the three-dimensional architecture. So it's not all bad news, right? Astrometry, they're not evil. They're our friends. Actually, Alex Venner, there who killed that other planet, is one of my students, so it's okay. What you can do is play the same game and actually constrain the orbit. So here's one, 221-420, where there was a really uncertain, very long orbital period. And so 2019, in that same paper with Stephen, we said, 62 years-ish, sure. Let me write a graph proposal and wait 50 years and find out, I don't know. And then a later paper came out with additional HARPS RV data we didn't have and said, this gray bars here, gray histogram, gave it a better constraint, but there's still this big long tail, right? Because it's in incomplete orbit. But then the Gaia people came along, or actually the same people used the Gaia constraint and got this lower panel here to rule out the super long periods because there was actually an astrometric detection as shown on the right. Yeah, another nearly face-on one, so it became a big thing. It's 23 Jupiter masses. Alex Venner, again. He's a beast, he's my student, he's awesome. And I'll forgive him for killing some of my planets. So here's one where it's actually good news. So here's one where astrometry did save the day and help us. So on the left, you see a bog standard RV plot. Lots of dots is what we do. I've been doing it for 20 years. That's all I know how to do. Kindergarten, right? With crayons. So 22-year giant planet. You see the orbit here. It does this kind of there for the Zoom people, like that. And with that eccentricity, we were actually able to constrain it, even though the orbit was pretty long and not 100% complete. So it was an awesome, fun result. We combined data from lots of different instruments. And this is my other student, Adrienne Errico. She was able to sort this out. And it's a 22-year super eccentric giant planet. Same deal, right? You get a minimum mass from the radio velocity as well. On the right side, you see that you can actually get a non-detection from Hipparchus Gaia. So Hipparchus Gaia astrometry, in the previous plots, yeah, you had a detection. You could actually tell that there was a wobbling going on. In this one, you could say, no wobble, no detection, no astrometric motion within a certain limit. You put an upper limit on the mass of the thing, right? That's what we want. So the astrometry posterior in the black dotted line was able to rule out the really high masses because you would have seen it do its astrometry thing. And the RV, of course, gave us a minimum mass, that's given by the red line. And you mash them together and you get the gray histogram, which was able to give us a real constraint on the mass to say, look, we claim it's a planet, it's a legit planet, it's not one of these crazy stars, it's, it's a quarter solar mass and face on, no, it's a real planet. And that's important for statistics, right? Legit planet in a low orbit, these are rare things, so it's a fun result. Okay, so every astronomy talk has to have this statement. Here it is. Gaia will save the day. All right, people have been saying this forever. I will say it now. So DR4 will drop, of course, more epoch astrometry, and we can play this game for all the things, right? So you'd love to do this same game for all the cold Jupiters that we know from RV and find out, are they really legit cold Jupiters or are they really, M dwarfs on face on? What's going on? So we're keen. Everyone else is keen. I'm sure everyone has got their codes ready for DR4 to drop. Ready to do that. And we saw in the previous slide, you don't even need a detection. You don't need an actual astrometric orbit to say something. So this is cool, right? We can actually do something with all 170-ish cold Jupiters and constrain their true nature. And that's important. Why is that important if you're still awake? Never can tell on Zoom. It's important because this concept here, Jupiter, friend or foe, this title of a series of papers written by my mate John T. Horner. And here's the idea. So back in '94, and some of us are old enough, again, the gray hair shown, some of us are old enough to remember this, where comet Shoemaker-Levy 9 slammed into Jupiter. And it was, obviously a fun event to see, but it gave people the idea like, oh, that could have been us. Good thing it hit Jupiter, not us. So that kind of spawned this concept that maybe Jupiter is actually a shield that kind of hoovers up things that are meant to hit the Earth, because it's first. Giant planets are giant. Remember point one? They're giant. So the gravity would suck in all the comets, or enough of the comets that would hit Earth to maybe protect us, right? Jupiter's a shield. It's a very lovely fairy tale, but as like most things in science, it's never that simple, right? So, but because we're scientists, we can test this with computers, fortunately. So we can train rocks to think in the form of silicon and simulate these things. So you might ask, what happens if I change Jupiter? If Jupiter is a shield and it protects and sucks up all this stuff, if I make Jupiter bigger, then it should suck up more stuff and keep it from hitting us, right? So if I make Jupiter bigger, on the left panel here, Jupiter's mass gets bigger, the number of impacts on Earth should be less if Jupiter is a shield. If Jupiter is actually a foe, right, consider the counterexample, what if Jupiter is actually sending stuff our way? Then if you make it bigger, more influence to fling rocks back at you, you make Jupiter bigger, Earth gets hit more. It's an easily testable thing, right? Straight lines, even I can handle that. So okay, just do the simulations. Again, this is actually quite old result at this point from 2008, but the concept is simple, and simple is often the best. So here's what really happens, right? On this lovely SuperMongo plot, SuperMongo, I still use it. So you do this, you simulate Jupiter from 0 out to 2 Jupiter masses. Yes, you can get rid of Jupiter and see what happens. How often does Earth get hit? So if you get rid of Jupiter entirely, you get this very tiny red dot on the left where you get fewer impacts. It's not 0, but it's less than you would get at the real Jupiter, which is here at the 1 in the middle. And if you make Jupiter bigger, things will change a heck of a lot. Make Jupiter smaller, an interesting thing here. You make Jupiter smaller, you actually get twice as many impacts. So that was a bit different. What if you change the eccentricity of Jupiter, right? The real Jupiter has an eccentricity of 0.05-ish, the black line. If you made it, in this case, John T did only a small number. I want to do this again with bigger numbers, but okay. If you make Jupiter more circular, the green line, things will change a heck of a lot. If you make Jupiter more eccentric, the red line, then things change a bit more. I want to find out, actually. We make it like 0.3, 0.4, but job for another day. So the upshot is basically, if you mess around with Jupiter, it's not a clear-cut thing that Jupiter is a friend or a foe, right? If you get rid of it, you still get whacked, although not as much. In fact, if you got rid of Jupiter, you have fewer impacts, so maybe Jupiter is actually chucking stuff at us. If you make Jupiter smaller, you get a whole lot more impacts. So why is this important? Well, you see it varies with the mass, it varies with the eccentricity, whether Jupiter is helping you or hurting you. And so with the RV plus astrometry constraints from Gaia, we'll get real masses. The RVs, of course, give us real eccentricities. And so we can actually get a better handle on these numbers. And then see where it's going and run the simulations. So why do we care about being hit? Well, it's not all bad, right? Earth does need to get hit. So formation of the Earth, and I'll try to play this. Get a classic result here, where, as you know, Earth formed kind of here inside the water ice line. Where'd the water come from? It had to come from somewhere. So we were once before a desiccated hellscape, might be again. Ask me in 20 years. So the that water had to come from out beyond the snow ice line, which is blue dots in this nice cartoon here. Where did that come from? Well, this shows that maybe Jupiter has some role in mediating this. So in this plot you see on the right, just a simulation of the formation of the inner planets. Jupiter actually mediates and delivers water in, right? You start out with a very dry, 10 to the minus 5 water mass fraction. You end up with present Earth, which is about 10 to the minus 3 ish, right? There we go. That nice pretty blue. So that's where the water comes from. It came from, among other things, Jupiter again, being a big hefty beast, sending stuff our way. So we would like some impacts. You don't want zero impacts. We're very tiny number. I want some. How many is some? Good question. So here's some other simulations where you form Earth with a Jupiter present in various places and see what happens. Trouble is, you actually, it's hard to get the right amount of water, right? The planet people, the transit people particularly find planets that have a lot of water. Water worlds, it turns out, are really common. So you say you find a planet with 2 Earth masses, it's got like an Earth mass of water. That's a lot of water, right? The Earth is pretty dry, right, to the minus 3. So if we had 10 times the amount of water, then maybe we don't have any land, and that's less useful for the kind of life that we would like to see, right? Trees and salamanders and whatever. Depends what you're after. So all this means is that it actually matters to some extent how often you get hit, which means it matters what is the size and nature of your Jupiter that's throwing stuff at you. So we'll need a bigger boat. So what we can do is design our universe. We'll design our universe with knowledge acquired from the universe, from Gaia, from RV, getting our masses, eccentricities, knowing what these systems are like, we can set up an n-body simulation, right? So what we want to do is take these real cold Jupiter systems. We don't know what Earth-sized planets are in there. We can't detect them yet. We know there's a cold Jupiter, okay? Take these systems, we got the real masses, real eccentricities. Now we can feed that into a computer and put in a bunch of test particles and ask, if there's an Earth there, how often does it get whacked? And then maybe you could include debris belts from our debris disk friends. Got a few of those people, they're nice people. You run it for 100 million years, count how often the Earth gets hit, and say, okay, maybe this system, any Earth-like planets are gonna just get too much water, or this other system, it won't get enough. So it'll be interesting to find out, because then you might say, okay, this one system, the terrestrial planets would have 5 Earth masses of water or something stupid, and you end up with what's on the right from Interstellar, which is not a fun planet, or maybe they didn't get enough. It's another data point. I think it's interesting. And it doesn't cost anything to do, right? It's just computer time. So, okay. Now, the other part, and this is sort of related to the journal club from yesterday, which is why I made everyone read that paper. Planning ahead. So I like big planets. I also like big telescopes, and spaceships especially. So as we all know, Habitable Worlds Observatory, or LUVEX, HabEx, HabWar, whatever, it's going to go up, right? The decadal told us to make it happen. So at some point when I'm old and gray, or older and grayer, it will go up. And we want to find out imaging rocky planets in habitable zone, right? We want to find Earths. And I've been trying to convince you all in this talk, Earths are great, but Jupiters matter. Jupiters are important if you're trying to find the Earth. So what LUVEX will do is target, say, 100-ish nearby sun-like stars. We want to find out, okay, which are the best ones? What are you going to prioritize? So because Habitable Worlds Observatory, HWO, is an awkward name, I'm Australian, it's Habo. We like shortening words and adding an O on the end. So, let's go have a smoko and a coffee. Let's go to the servo and put some petrol in the ute. Let's launch a Habo. We're gonna launch a Habo, but we got to know what to point it at. So this is a paper that I did in Journal Club yesterday as a sneak preview. and then there's the sort of signature plot in the middle. And for those who weren't there or didn't read the paper, it was a long one, I'm sorry. The upshot is the stars that Habo is going to look at are nearby, sun-like. People have been looking at these stars for decades, right? For radio velocity planet searches, they're good planet search stars. So, okay, there's lots of data. So this paper, what they did was just grab all the data that they could get their hands on and ask, okay, what planets can we exclude in these systems? What do we know about these systems? Let's characterize the heck out of them. A lot of them had known planets. They were able to refine orbits. Some of the planets they were able to destroy because it turned out that those signals were not planets, but they were actually stellar activity. Okay. Catherine killed one of my planets. Okay, she verified a couple others. You win some, you lose some. This plot is showing the sensitivity that the current data have to planets in the what they call Earth equivalent insolation distance, which is a long way of saying habitable zone without actually using the H word. Okay, just means how far from your star do you need to be to have a good shot at having Earth-like temperature, kind of dancing around the habitable zone word. So obviously for the sun, that would be 1 AU, but stars are different temperatures. Okay, what you see here is that for a good chunk of these, like about half of them, more than half, you can't exclude a Neptune just swinging around in the habitable zone. It could be there, we wouldn't know it. Some of these we do so badly, you couldn't even exclude a Jupiter. There could be a 300 Earth masses of gorilla running around in there, you wouldn't know it. So there's work to be done, right? I would like us to clear these systems of these sorts of interlopers before we point a $20 billion telescope at it. Call me crazy. So this is the damning sentence I put in the bottom here is, we are not sensitive to even Saturn mass things, let alone smaller stuff. So, and of course, you put this in your grant proposal, by the way, highlighting the need for future vetting efforts for EPRV, extreme precision radio velocity. By the way, the spoiler is it does not have to be extreme. So, okay. So one giant planet at 1 AU is going to ruin your whole day if you're on an Earth-like planet in that orbit. You're going to have a bad time. This plot up here shows examples of kind of moderately eccentric giants, and they don't even have to be listed as one Jupiter, but you could do a Saturn mass, it would still ruin your day. What it's showing is that with the obvious, right? If you have a somewhat eccentric giant planet hanging around and whipping through your EEI habitable zone in the green dashed line region, then anything else is just going to get disrupted. It's going to get whacked, thrown out. Not good. Here, red is bad. Red means it's disrupted. So, so as you might guess, I would like to rule out such objects. And such objects hanging out, around 1 to 2 AU are fairly common, right? It's ish. They're not, half of all stars. It's more like 10 to 15%, depending who you ask and what bins you use, but they're common enough that you should be worried if you're looking at 100 stars. Right? You actually have to think about it. So now here is, I'm going to contradict myself. That's what I do best. Guy will not save the day. I know everyone is shocked because every astronomy talk has Guy saving the day. In fact, I did about 15 minutes ago. Here, Guy will not help us. Why? Well, I care about planets that are hanging out in orbits of like, in like half an AU out to like 1 or 2 AU, right? Thinking something like that. That's great. That's not really what Guy is meant to do. They're too close to the star. So you see this plot here. It shows the astrometric sensitivity of the next Gaia release as a function of your orbital separation. As you would expect, Gaia is going to be having a sweet spot from, like 3 to 10 AU. That's the sweet spot everyone's talking about. That's the Jupiter analogs, which I also love. So I'm keen for that, but that's not going to be helping us for this mission of trying to rule out the disruptive giants. So there's no way around it. You're not going to get it for free from ESA. I'm sorry. You have to do it yourself. And the way to do it yourself is you just gotta buckle down and observe them. Okay, I'm an observer. That's my solution to everything. Go observe. So, okay. The best time to do that was 20 years ago. Second best time is now. It's like planting trees, going to the gym. Best to do it when you can. So, that's the summary of that part is we have lots of RV data and they're good data, right? There's nothing wrong with it, but you know, I claim the data are cursed. They're not cursed, but I like using Simpson's reference. The data are great for what they were meant to do, but I would like it to be higher cadence. And really cadence is king. The trouble we're finding is you get those horrible sensitivities because you have giant gaps in the data sets, you have different instruments, there's offsets, all kinds of stuff that is not good for this sort of thing. That's fixable, right? We can fix this by observing it more. So let's go do it. So it takes a lot of data, right? So if you want to find these sorts of things, there is really no substitute for cadence. You just have to bang away on your stars and do it. Well, that's great, but unless you want to give me 300 nights of Maroon next time to do this, no. Okay. I'll shout you a beer.
2 beers.
2 beers. Okay. So yeah, this is hard to do, right? You can't convince a TAC to do this for 10 years. And you really can't convince a grad student to do that for 10 years either. So you need someone like me who is a little more patient. In this case, I was actually impatient and I got sick of applying for time, so I built my own telescopes. So I built my own telescopes. There they are. I got tired of applying for time. I got tired of being rejected. So I said, nuts to it. I'll build my own. And here they are. So what you see is the Minerva Australis, fancy shirt here, Minerva Australis telescopes. There are multiple small ones. In this case, we now have 5. And inside this rather ugly building is our spectrograph. It's actually a Kiwi spec. It is literally the same as Maroon X, but not as good. But it's the shiny torpedo tube thing, and it's good spectrograph. So what's a Minerva, you might ask? It came from this OG version that we built in Arizona in 2014, 2015, Miniature Exoplanet Radio Velocity Array. It's an acronym that actually doesn't suck, unlike many in astronomy. So there you go. And the 4 of us got together a while ago and basically had the same idea. It's like, we need to bang away on these stars to look for small planets, but we can't get enough time to do it. So let's build our own. We built our own. Very pretty picture. So how does it work, right? I get this question a lot. So basically, you have 4 telescopes or 5 or whatever, commercial, off the shelf, 70 centimeter. So you just buy them, red check, you buy it. And you have a very familiar looking photon torpedo tube here. And then you just connect your fibers from all your telescopes into your spectrograph. It's all pipes, right? Somehow it turns light to science. That's for smart people to figure out. But the question I always get is interferometry? No. No. I have 4 telescopes. What you see here, not a very good one, but each fiber puts a different trace on the detector. And so you end up with, say, 4 telescopes, 4 spectra, 4 radio velocities at the end of the day, which you can then, you know, combine and spin up to your heart's content. That's what it is. Why is this important? So it's important because it saves us money, right? We're cheap. We're not lazy, but we are cheap. And so the idea is that small telescopes will give you the same amount of light as an equivalent larger one, but for cheaper, because if you wanted to buy a single 2-meter telescopes, that's stinking expensive. But if you buy 6 70 centimeter telescopes, cheaper. So, and they're also off the shelf, right? There's a little bit of factor that builds them. And so it's a bit more uniform. So more cost effective, you retire some risk, time-wise, it's actually a bit faster. Everything works. So I got my friends together. These are some of my friends that I got together who believed in me and gave me suitcases full of cash to make it happen. So, and thank you, all you friends, especially the ARC who gave us 800 Gs to build a spectrograph. And that's great. And so we have it, right? It's been on Sky for 5 years now. And it gives us PRBs, precise RBs, for nice stars down about 11. It does what we want, and we do what we want. Fine, you know, it's good to be the king. And I can just say, I want this target, and we make it happen. I like doing that. So I've written a proposal in 5 years. Okay, we can hammer away on the Habo targets until the wallabies come home. That was the end point, right? And here's why I want to do that. What you see here is some simulations, fake data. So on the left side is actually real data for a given star from that paper that I showed earlier. That shows how badly the current state of play, how bad it is, right? So if you look in the green box, you know, the habitable zone, but we didn't say habitable. Green zone. You see, on the left is the mass sensitivity, okay? So in the green zone, we're only good to like 100 to 200 Earth masses. Below that, we're blind. The black line here is the 50% detection threshold. Below that, we're missing half the planets. So that's not good, right? That's basically, you're missing a Saturn mass planet that could just be barreling around in there, you never know it. Okay, well, I'm gonna go observe this star for 3 years. I'm gonna hit it every 10 nights for 3 years. I can do that. It's my telescope. I can do what I want. So I simulate that. I do RV search, same game that the paper did here that Catherine wrote, and you end up with getting that limit down to about 20-ish. 20-ish Earth masses. Oh, there's a question.
Where does it appear to get worse at larger distances on the right one?
So what you see on the left is a long string of data from many observatories going back 20 years. On the right is strictly the new data. I have not included the old data at all. And so that's, but in this case, for this science case of just the green box, I don't care about the long period stuff. So this is sort of a bizarre case where adding or including only the new data and not even trying to include the old data actually made it better. A little counterintuitive, I know. I think it has to do with the offsets to the instruments, adding some uncertainties and the gaps, data clumps, all those kind of things that really mess you up. Whereas here, it's basically 3 years of, I'm banging away on it every 10 nights. Obviously, you're gonna get hit with weather, you're gonna hit with seasons. It's all in the simulation. But the short version of this is, hey, look, we can actually make a difference in 3 years. So what I'm working on now is playing this simulation game for different cadences, different assumptions, all that kind of stuff. So stay tuned for one of these years for me to finally write that paper. But that's the sort of the signature plot of why you might want to do this and why you might want to use a telescope like Minerva, which is, of course, my telescope, and it's not super precise. You don't need 30 centimeters per second to do this. In fact, in that last simulation, I simulated like 5 meters per second precision. We can do better. We don't have to have crazy precision. We just need time. Who has time? I have time. Okay. And then just, again, you can tell this is basically a grant proposal that I put into a talk, all right? Is, okay, can we do it? You run the numbers, you blah, 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 run the numbers. You know, bright stars is pretty easy to do with our telescope. And I think the real place where we win, because the stars are so bright, and I have 4 telescopes, I don't need all the photons from all 4 to really pin down the RV down to super precision. I don't care that much. I can get away with 5 meters per second in this case. So why don't I take all 4 telescopes and formation break? Have them all point at 4 different stars. Why not? Then I can go 4 times faster. Okay. So then you suddenly get down to only 186 hours of wall clock time to do this. We can do that, right? 24 clear nights a year. Even we get that, except in La Nina year, but we get that. So bottom line is we can do it. It's not a huge burden on the operations. And that's important if you're writing a proposal. But why do you want to do this, right? Let's get back to why. The why, of course, is you want to characterize these stars now so that when people are selecting targets and scoping out, speccing out the mission, and working out all the details of the mission, you want to know how many stars you got that are actually useful and all you can about the stars, right? So you want to actually block out the stars that are going to have some Saturn barreling in their region of interest. So, okay. Star limit is $1 million saved. Probably a lot more than that. Now, that's why that's important. So once I do that, I will expect a check from NASA. That's 20 years down the road. So conclusions, right on time. Conclusions are that giant planets actually do matter, even if you are interested in Earths. They actually do matter because even though everyone's chasing the smallest planets, you got to consider the influence of all the outer giants as well. And also, self-serving, I know, but those of us who cannot do EPRV or even PRV, just regular RV, it still has a role in our EPRV world where everyone's talking about 20 centimeters per second here, there, and everywhere. And I feel like a chump with my 5 meters per second small telescopes. We can still do something valuable. So hopefully we can do it. And that's my conclusion. So thank you.
Thank you, Rob. That was fun. We have some time for questions, so feel free to ask the first one.
Okay.
Thank you very much. Out of curiosity, you show us the plot of how many hits you get if you change the orbit of Jupiter a little bit, use side string. But on our system, we have like Jupiter and Saturn. That makes a mess, or that helps. Or...
Yeah, I guess that's, if you want to do the survey again or this simulation again, why not include Saturn? I think, okay, so the plot I showed was from a 2008 paper, so you can imagine that computers got a lot better since then. So there's certainly still
some resonance that helps to remove, or
like the interaction of Jupiter and Saturn.
Yeah,
that's true. That's an interesting point. And those friend or foe papers that Jonty wrote yonks ago did not even include a Saturn. They just had a Jupiter, and then you move Jupiter around and change the size. But yeah, it'd be fun to go back and put in Saturn, right? Why not? We have technology, and then do more test particles and all that. So I think we should do that, and that's just get a student to do that.
I had a question basically on the same thing. So you see like a little bit of like an anthropomorphic dip there where the eccentricity that Jupiter is, the number of impacts is minimized. I'm wondering, has it been done or plan to be done to change like the Earth Jupiter distance or the distance of Jupiter away from the sun, or vary the mass of the sun, or things like this, just to see if we can solidify the anthropomorphic principle?
Another good idea. We've got all kinds of good ideas for the next run of simulations, but I'm trying to think, because there's 4 papers this series. I don't know if they've moved Jupiter around. No, because Jonty's a small bodies guy. He was more interested in like asteroids and the Trojans. He's my mate. We work at USQ together, so I can just go back and say, "Hey, Jonty, let's do this." So yeah, that's the thing we can do, right? We can move it from 5AU, and let's move it over here and over there, and yeah, we can totally do that. Interesting about changing the mass of the sun. I have not thought about that, what that might do. There you go, that's another dimension. These are all good ideas. We'll write them down and go back, and we have some projects to do.
Still make the plots in SM though.
Yes,
That'd be great.
You can't beat SM, you gotta do it.
I agree.
You showed us that plot that disrupt Earth orbits. It was one of the slides.
What with the red and the blue?
I just want to see if you change Mars into Neptune, would
This
that
one?
disrupt Earth? Yeah. So what is there on the y-axis in the middle plot?
All right, so this was made for a proposal, so it's not even in the paper, but, all right. I didn't explain it very well. Okay, so the center plot is where, let's see. Obs, I think obs means obstacle, perhaps, I don't know what Sarah meant, but, okay, so on the left, you consider a system, I'm guessing these orbits. The green dashed lines must be things like inner and outer habitable zone boundaries. Black ellipse there, of course, is an 0.3 eccentricity planet, just kind of a top-down view. Center plot is what if I make the disruptive planet at E of 0.01, and the right one is if I make the same planet E of 0.3. So the left and right plots. So what you see on the right plot is fraction of OHZ. Oh, optimistic habitable zone. Okay. Optimistic habitable zone. Fraction that is stable. Blue is good, red is bad. So 100% stable in the blue zones. And then, okay, obs. Subscript obs is meant for, but I'm guessing that's where you stick your giant planet at 1 Jupiter mass. MP comma obs. Sure. So if you stick a giant planet way the heck out here at 4 AU mass, helps to read the plot. Hey? It's too small for you guys to see, but so okay, I think that's what's going on is you look at the right and I say, okay, I have an E of 0.3 planet and I vary its position and its mass. How does that affect your habitable zone stability? You just run it a gazillion times. So stick it out at 4 AU, it doesn't matter how big it is, no one cares, right? It's all blue. The inner planets don't care. Stick it at 2 AU, then you're gonna have a bad time. You lose half your planets in the habitable zone. Obviously, if you stick at 1 AU, you kill everything. And this just shows that, of course, the intuitive result, if your interloper giant planet has a higher eccentricity, it just trashes things, right? So you get more red as you increase eccentricity.
So the middle plot says if Mars had a Saturn mass, it would probably disrupt Earth, but maybe not Neptune. It doesn't go to low enough masses, but.
Well, with nothing to do with Mars, but
No, I'm looking at distance at like 1.5
Oh, yeah.
for instance.
Okay,
and
yeah, if
then
you stuck.
masses. Jupiter would disrupt it, Saturn probably, maybe not Neptune, so we could survive with the Neptune.
yeah, if you stuck it, okay, yeah. So Neptune must be down here. Yeah, it'd be in the white zones.
Maybe.
You get 0 point, so you might get half of them. You okay? But yeah, if you make 1.58, let's say you make Mars equal to 2 Jupiter masses or 3 or 4, then you're gonna have a bad time. Yeah.
Have any questions online?
Anybody online?
No questions from
Anybody
anyone?
online? Okay. Questions here? Yeah.
How much Minerva Australis costs? And do you want to have that on the north so you can cover more stars?
We didn't put my NORLab thing in there. I'm literally at NORLab. Okay. All right. So how much does it cost? The answer is, if you're an American and you want to apply for Minerva Australis time, $0 because JPL paid for it. So call for proposals is coming out any day now. So yeah, propose for time. But how much did it cost to build? That whole schmear was about 6 million Australian, which these days is about $3.50 American. Now, the exchange rate is horrible, but 6 million Australian is on the order of 4 million US dollars to build, the building, which was overpriced because some racketeering or some, I don't know what the heck was going on with that, but graph or something. But yeah, basically the building would cost more than it should have. The spectrograph was $1 million. Each telescope was about 300 grand Australian. And the domes were about 50 a piece. So the real killer was the building, and I think we really got focused on that. 6 million.
We have 4 telescopes, but 5 platforms, maybe a sense about the 5th platform.
I built 6 platforms because it was a nice, I wanted to have 6 telescopes, because then we had 6 spots for fibers on the detector, but I ran out of money. So we have 4 telescopes. We just got a 5th one installed last month, thanks to another project that gave us their telescope. So we have 1 extra platform if someone wants to give us $250,000 and finish it out. So, yeah.
So that's gonna add another order in the.
Yeah.
Oh,
So they'll be starting the next semester 24A for Noir Lab time that you can apply for. We'll have access to 4 0.7 meters and an 0.8 meter that will all feed into the same detector, and you can go wild.
have your own observatory.
It's good to be the king, yeah.
Well, thanks again, Rob. It was a great talk.